Okay, we have here matrix. I'm not going to read the entries to you, but I will say then that the rows of this matrix can be regarded as three vectors, okay? And the span of these three vectors is what we call the row space. We want to see what the span of these three vectors might be. Now, we're going to actually figure out the span of these three vectors by first reducing this matrix to this form. And of course, there is one more step if we want to get a complete reduction. We would multiply this row by -1, but the matrix I gave you was this one, and this one works just as well for our purposes as it would if we had the 0, 1, -3 here. Okay, well, what we do is we take this matrix and we reduce it to this matrix. And we want to show that the rows of this matrix span the same space that the rows of this matrix do. And the way we're going to show that is that the rows of this matrix can be combined to give us this row. They can be combined to give us this row. They can be combined to give us this row. They can be combined to give us any of the three rows, which means that each of these rows is a sum of multiples of these rows, which means that the span of these three vectors is the same as the span of these vectors. That doesn't quite prove what I just said, but we're going to get the idea. Okay, there's one little detail that would have to be established there. Okay, so let's think again now. The rows of this matrix are 2, 4, 8, 1, 1, 7, 1, 3, 1. Now we regard these rows as giving us, each row is giving us a vector, and we'll represent the vector as a column. So the 2, 4, 8 row, when represented as a single vector, will represent as 2, 4, 8, column vector 2, 4, 8. And 1, 1, 7 as a column vector 1, 1, 7, 1, 3, 1, column vector 1, 3, 1. Similarly, these vectors will be represented as column vectors, and you'll see that right here. If we want to look at whether, let's say, well, we start by looking at whether this vector, the 2, 4, 8 vector, can be represented as a sum of these row vectors. Okay, well, the vector 2, 4, 8, the row vector 2, 4, 8, will represent, or the row 2, 4, 8 gives us a vector that we'll represent as the column 2, 4, 8. The row 1, 0, 10 here will represent as a column with 1, 0, 10. And this row as a column with 0, -1, 3. Now can we add multiples of these rows? Of course, the third row could be represented as the column vector 0, 0, 0. If we want to do a sum of these three vectors, arbitrary sum, then we're going to let C1 be whatever we want to multiply the first row by, multiply the second row by C2. Now we could have a C3 times the third row, but that wouldn't give us any information at all, since anything times the row vector we have here would give us just zeros, wouldn't add any information. So we're just going to not even mention this third row. So a sum of multiples of the first two row vectors, or the vectors corresponding to the first two rows, would be this. C1 times the vector corresponding to this row, plus C2 times the vector corresponding to this row. Now we're testing whether a combination of these two rows can give us this row. So we set that equal to the 2, 4, 8 column vector that represents the vector of this row. Now you might be wondering why we use columns here and not rows. We could actually do that, but we're more used to seeing vectors as columns. So we're just going to kind of translate these rows into columns. Okay. Now, if we can solve this sum for C1 and C2, then this vector is in the span of these two. So we write down the augmented matrix that corresponds to this matrix equation, and we can reduce this matrix. Now I didn't reduce it, but you know that this matrix could be reduced, and when it does reduce, the third row goes away. 10 times the first row subtracted from the third. Then we're going to do 3 times the second row added to the third, and we're going to get 3 zeros here. In that case, we have a solution because the bottom row is all zeros. That doesn't contradict anything we get from the first two rows. The first row tells us that C1 equals 2. The second row tells us that C2 equals -4. Of course, we'd have to multiply it by -1 to put it in the form where it reads C2 equals -4, but that's easily done. As it is, it reads -C2 equals 4, and that's equivalent to C2 equals -4. Okay, well, in any case, since this matrix reduces down to something that gives us a solution, C1 equals 2, C2 equals -4, last row 0 equals 0, so everything's consistent. We see that this first row is a sum of these two rows. So the column vector 2, 4, 8 is in the span of these three row vectors here, expressed here as columns. And of course, we don't really need to include 0, 0, 0. We could just say it's in the span of the set consisting of just this vector and this vector. Okay, if you think about what dimension means, it's very clear that this vector is independent, linearly independent of this vector, since this vector is not a multiple of this vector. So that the dimension of the rows of this matrix is 2. Now, we can check to make sure that this row is also a linear combination of these two, and this row is also a linear combination of these two, so that these three row vectors are linear combinations of just these two vectors. That means that the space spanned by the three rows of this matrix is two-dimensional, just as the space spanned by just these two vectors is obviously two-dimensional. So the dimension of what we call the row space, the span of these three vectors, is 2. Not only that, but these vectors constitute a basis for that span. Okay, we're not sure which two of these vectors we might want to use for a span. We'd have to check. We'd have to pick two that aren't linear multiples of one another. And that would be easy to do. But the big point here is that if we row reduce a matrix, it doesn't affect the span of the row vectors. So the row vectors we get at any stage in the reduction span exactly the same space as the original three vectors. So that's kind of a big deal. So my statement here is that row operations don't affect the span of the row vectors. Turns out they don't affect the span of the column vectors either, but we'll get to that in a minute. So the span of the row vectors of this matrix and the span of the row vectors of this matrix are identical. Anytime you do an elementary operation on a row vector, on a matrix, you don't change the span of the set of row vectors. And there's a very straightforward, concise statement that we can make that shows why that is, and I'll discuss that in the next video.